For 1c, we have a second line called L2. It has this equation. The resultant vector r is going to equal the position vector 2, 11, negative 7, plus some scalar s times p, 0, negative 3. We're told that L1 and L2 are perpendicular, so we must show that p equals negative 3. This is a show that problem, so this we're kind of thinking is like the answer that we're supposed to get after doing a bunch of work. We're not going to start with p equals negative 3, so I'm not going to plug it in, but I'm going to do some work knowing that these two are perpendicular, and hopefully I'll get p equals negative 3. So let's write down that equation for L1. L1 is going to equal the resultant vector r, which is equal to 4, negative 1, 3, plus some scalar t times the directional vector 2, 6, negative 2. And if I know that these two are perpendicular, then I could take the direction vector of L1 and take the dot product of that with the direction vector of L2, and that should equal 0. I don't really care about these points, these position vectors, because I just care about the direction of this line and I care about the direction of the other line. So really, if I compare those two vectors together, that's all that I need to take the dot product of. So let's do that. Let's take the dot product of L1, of the direction vector for L1, 2, 6, negative 2, and we're going to dot that with this direction vector, p, 0, negative 3. And knowing that they're perpendicular, the dot product should equal 0. So then let's take the dot product. 2 times p plus 6 times 0 minus 2 times negative 3, that equals 0. So I just took the dot product, multiplied my x components, my y components, my z components, and I added them all up. So combining all this, I get 2p plus 6 equals 0. If I do a little bit of algebra here, subtract 6 from both sides, I get 2p equals negative 6, or p equals negative 3. And what do you know? I was able to figure out that p does in fact equal negative 3. This one's good.